Hello, friends. Welcome to this month's webinar. I'm Ram Lakshmanan. So I'm the architect of Ycrash product suite. So in our previous month webinar, we spoke on the topic common memory leaks and how to fix them, right? And this is a sequel, or this is kind of a continuation to a previous month webinar, which is not so common memory leaks and how to fix them. So in the chat, we will share the link in case if you couldn't attend the last month's webinar, we are sharing the link of the previous month's webinar, so you can take a look at it, right? Offline. Okay. So let's move forward. Okay. So friends, in this webinar, we are going to be talking about some of the memory leaks that is not very common. So we are going to be talking about 3 such scenarios. So the first memory leak scenario, which is not very common, that we are going to discuss is the mutable keys in Java collections. How keys which changes in Java collection will result in a memory leak, right? Let's look into that. For that, let's look into a sample Java program, which is going to simulate this problem, right? Let's look into that. Okay, so this is that program, what I have. So friends, look at this. Here I have a user class, right? So this user class has an instance variable or a member variable called as a name, right? And then it has a very valid hash code and equals implementation. So these two methods needs to be implemented, especially you are working on the Java collections, especially in hash maps. To insert the records and retrieve the records, hash map uses these methods. It has to be properly implemented. And these two methods are very properly implemented. There is nothing wrong with that, right? So now let's look into that actual program where this leak is happening, right? Let's look into this. So here, we have a main method. Here we are instantiating an hash map, right? We're creating a hash map. So let's see what we are doing here. Here inside this while loop, right? Here there's an infinite while loop. Here what we are doing, we are creating a new user object. And for that user object, we are passing the name as Jack plus count. So initially the count is going to be 0. So this user object, we are setting the name to be Jack 0. Okay. And then once we created that user object, we are inserting that user object into the hash map, right? We're inserting the user object into the hash map. Okay. Look, here is something, we do something interesting. That is, we mutate the key. That is, we change the key, right? See, look at this. Here I'm changing the username from Jack 0 to, I'm calling it as a Jack and Jill 0. And I'm doing it after inserting the record into the hash map. Okay. So now, friends, look at this code. Now, after I inserted the record, here I'm inserting the record and here I'm changing the name. After doing that, look what I'm doing here. Here I'm removing the record. See, now I'm removing the record. So my name was Jack and Jill. If you see this hash code implementation, this is what I'll talk about what is the significance of hash code and equals in a moment. But here, if you see, I'm now removing that record, Jack and Jill, right? Just to be safer, I'm also removing this record with the original username, Jack 0. So I'm now trying to delete the record with both the names that I gave to this user object. Okay. And now I'm going on a loop. So once again, I'm going to create Jack 1. I'm going to keep doing this. So when I run this program, will it result in a memory leak or not? So people who are there in the call, you guys can put your answer. When I'm going to run this program, will it result in a memory leak or not? Because here I am inserting the records and then I'm removing the records. Will it result in a memory leak or not? You guys are willing to share, put any message in the comment, right? Okay. So friends, by looking at this program, it shouldn't create any memory leak, right? Because I'm adding and I'm deleting both the records. So hash map size should never grow, right? So let me run this program. Let's see what happens. So now I'm running this program. Here for every 100,000 records I'm inserting, I'm printing the size. See, let's run it again. See, you can see the size is growing. It kept on growing, and once the hash map size went beyond my XMX limit, it resulted with this out of memory error Java heap space. So why is this happening? But because isn't that this shouldn't remove the records? Why the hash map keeps on growing? Like it's going to several million records. Why it is doing that? Right? So to answer this, let's see, we have to understand how the hash map works. We have to understand how the hash map works. So let's dive into that. Friends, hash map internally has an array of buckets, right? It has an array of buckets. So bucket 1, bucket 2, and bucket n, it has array of buckets. And within each bucket, it has a list. Within each bucket, it has a list. So for optimization purpose, for doing a faster lookups, when someone tries to insert a record into hash map, when someone tries to insert a record into hash map, what does the hash map does it tries to invoke the hash code method. There is this method called hash code method on the object which we were trying to insert. So based on that value that we get back, based on that value it get back, the hash map determines in which bucket this record should be stored. That's how it has implemented. Based on the hash code value, what it returns, it determines which bucket to be used to store the records. Okay. In this case, let's say for this user object, let's go back to our user object here. See, the hash code implementation is just saying on the string object, we are saying hash code, right? Now, and then look at this equals operation, what we are doing. We're just checking whether it is the same name, right? That's what we are doing. Now, let's come back here. Now, based on the hash code, it determines the bucket. Let's say for that user object jack1, which we are trying to insert, it's going to invoke the hash code on that object. Let's say it determines that based on the hash code, let's say it stores in the bucket 1. So it determines, okay, this is the bucket 1 it's going to store. Here the object is stored into this bucket list. And now once we are inserting, what we are doing in our code, we are changing the value. We are changing the jack x, that is the value to be. We are changing to Jack and Jill x. So the value is changed, right? So now this is how the hash map looks like. There is a hash map, which has an array of buckets. Within each bucket, there is a list. And within the list, we are inserted a Jack X, and now we changed its name to Jack and Jill X. Okay. So now let's see what happens. When I try to invoke this, remove the new user, Jack X, let's say I'm invoking this operation in the code. Let's see what happens. Now, friends, the hash code is going to be, method is going to be invoked on this user object. So say this one is going to return bucket 1, right? Because this is what is going to return bucket 1. Now, what it's going to do is, now this hash map is going to go to this bucket 1. Now, within this bucket 1, what it's going to do is, it's going to invoke the equals operation on every element in this list. It's going to invoke equals operation on every element in the list. So now it's going to come to the first element, and then it's going to check whether it is equal, whether this Jack X, is it equal to what is the value present here? No, here the value got changed. From Jack X, it got changed to Jack and Jill X. So this is not going to match. So it's going to return false. So the record will not be removed. The record will remove here because the equals method fails. Now, let's answer the second question. Why this method also is failing? Why trying to remove the Jack and Jill X is also failing? See, if I want to invoke the hash code on this Jack and Jill X, it's going to return me a different hash code. It's not going to be the same hash code as Jack X. So based on this, on a different hash code, maybe I will now start to look into a different bucket. Let's say I go to bucket 3. In the bucket 3, there's no records present. Right? There's no records present. Or definitely not that Jack X is going to be present. So now it goes there and it also fails there. So what happens then? The record got inserted. So and the remove both the remove operations are failing. Since both the remove operations are failing, the hash map keeps building up. When hash map keeps building up, when it goes beyond XMX limit, then you're going to get this out of memory error. Okay, you're going to get this out of memory error. Okay, now let's spend a little bit time. When this out of memory error happens, how to go about debugging the problem. Once this problem has happened, how to go about debugging the problem. We went into the details of this in our last webinar, but I'll just do a quick refresher here as well. Okay. So friends, once the heap dump happens, once the out of memory error happens, we want to take heap dumps to diagnose what is the problem going on. Friends, there is 8 different options to take heap dumps. So there's multiple, you can use this jmap command, which is there in JDK, or to your JVM itself, you can configure this argument, heap dump out of memory error and heap dump path, and give the file path. So that means whenever an out of memory error happens, the heap dump is going to be taken and then it's going to be returned into this file path. This is another option you can pursue, or you can use the JCMD, and there are other such options, right? You are welcome to use any of the option of your preferred choice. But my friends, see here, I'm here with you. So we are talking on the topic, not so common memory leaks. So you need to capture heap dumps. But in production, we always hear, oh, the application has crashed. Oh, the application has become unresponsive. The timeouts is happening, right? So when such production problem happens, right? We should capture all the artifacts, because if application is unresponsive, it can because of garbage collection process repeatedly happening, right? Or there is a backend slowdown. Anything can happen. So that's why here there is this open source script called that this YC data script. It is GitHub. It's available in GitHub. There is no licensing attached to it. It is an open source solution. So you can trigger the script like this, YC-P, give the process ID, the Java process which is in trouble. And then when you trigger it like this script is going to capture your 360-degree data from your application stack. So this data will be very useful to troubleshoot not only out of memory error, also any problems, let it be the garbage collection issue or threads stuck issue or a network issue, right? It is going to be very helpful. So when you trigger the script, it's going to capture a 360-degree data and bundle them as a zip file. So by default, the script does not capture heap dump, because heap dump is an intrusive operation, right? When you take an heap dump, it takes several seconds, sometimes even few minutes based on your heap size, right? So by default, it doesn't capture heap dump. If you want to capture heap dump, you need to explicitly pass this flag called -ht, right? So the intention is we don't capture heap dump to keep the script very lightweight. So if you trigger the script without heap dump, it will be completed under 30 seconds, and it will not add any word overhead to your application. And this will be a very vital information to troubleshoot the problems. Okay. See, now to troubleshoot out of memory errors, we need 2 artifacts. One is heap dump, right? Which tells what are the objects is there in memory, what are its references, and what's going on within your memory. And also we need one more artifact called as a garbage collection log. So the garbage collection log will help you to tell what is the memory pattern going on. If there's a memory leak, how will the GC behavior is going to look like? So that is an important precursor to look when diving into out of memory error. So for example, people would have seen this in the previous webinar as well. So this is a garbage collection behavior of a very healthy application. You can see what's happening in the garbage collection way. Look at this. You can see the memory is building up. When a full garbage collection, when this red triangle runs, the memory drops all the way to the bottom. And once again, the memory is building up, and a full garbage collection runs, the memory is dropping all the way to the bottom. You see this beautiful sawtooth pattern going on. Okay. Now, look at this is the garbage collection behavior of an application which is suffering from memory leak. You can see memory went up, it came down. It's going up and down, but these red triangles, they are not dropping to the initial point where it was happening, right? Here it was happening at a 4 GB, but look, as time progressing, the garbage collection is not able to bring back the memory to the 4 GB. It is now just keep on going up, and after a point, it just keep on repeatedly running, right? Friends, I've told this earlier, right? When one garbage collection event runs, when one full garbage collection event runs, just that one event, one red triangle itself will cause a CPU to spike up and down, because Garbage collection is a heavy CPU intensive operation because the garbage collector has to go through all the millions of objects which is there in memory, and he has to check what are its references, who is referring those references. It has to walk through that object tree to see what are the active objects, what are the inactive objects, and inactive objects has to be removed from memory. So it takes enormous amount of CPU cycles, right? So here, if you see, the garbage collector is keep on running. Towards the end, the garbage collector will keep on running to try to reclaim memory. Since it's not able to reclaim it, it will keep on running. When this happens, the CPU is going to be at 99-100%, right? The CPU is going to be continuously spiked up and it's going to be remain there. So friends, whenever there is a memory leak, the CPU will also spike up to 100%, but not the other way around, right? A CPU can spike up, but memory can still be at the bottom. But when a memory is leaking, the CPU will be always be at 100%. It is like when when husband is not happy, husband is not just happy, but when the wife is not happy, the entire family is not going to be happy. Right? When wife is not happy, entire family is not going to be happy. Similarly, when there's a memory leak, the entire JVM is not going to be operational. The CPU will spike up. Application will become unresponsive, right? Okay. Now let's come back. So we need garbage collection law to confirm the memory leak behavior. And then also we need to take a heap dump to see which is the leaking objects. So for this example, I got the heap dump. So for this program, I captured a heap dump. Let's review that. So you are welcome to use any heap dump analysis tools like Eclipse Mat, JVisual VM, JAT, right? And also you're welcome to use our heap hero tool, right? So here I got it already uploaded. The dump I had uploaded here to the heap hero tool. Once you upload the dump, the tool is going to present you what's going on. If there is, it uses algorithms to see whether any problems are happening, any memory leak patterns are happening in your application. If that is the case, it puts an alert at the very top. And here it is reporting. Look at this. It's saying there is a thread which is keeping the variable, it has local variables, which is occupying a size of 99%. So there is a main thread, because this is the main thread, which is what is executing. And it is having some local variables, because see, this hash map is a local variable, right? It's a local variable of this main method. It is occupying like 99.9% of memory, and all of them is occupied from this hash map. It is even pointing out which is that variable which is occupying, right? So now let's look into it. So friends, whenever there is a memory leak, always come. I'm going to teach you a very effective and simple technique. Whenever there's a memory leak, always come to this largest object section. There's multiple sections in the report. You don't have to go into all the sections. This is a very simple and effective technique. Come to the largest object section. In this largest object section, always, there's only two patterns. The first pattern is the first object is what responsible for the memory leak, because the leaking object tends to grow in size and it occupies enormous size. So always the top object is what responsible for the memory leak. And here we can see there is this main thread, which is occupying 99.92% of memory. So now, okay, I know, okay, this is a thread, but now I want to see the details. What is there in this thread? What is causing it to grow to 99.92%? To do that, click on this more icon and then click on this outgoing references. Click on this outgoing references. What's happening? Yes. So when I click here, it has opened this one. It tells me what are the outgoing references. That is, outgoing reference means what are the children? What are the children of this thread? What is it referencing to? So now we can see there is this main thread. It has internally has an hash map. And you see here the hash map. These are all the records within that hash map. Can this hash map is having like a 3.38 million records. That is how much records are present. The 3.38 million records are present in this hash map because we kept on adding and this remove didn't work. And now let me click on one of the node. When I click on one of the node, here I can see the key is the user object, right? So if you want to see, I can even see the name I added. can see the name I added is the Jack and Jill. What is the arbitrary number is there? And this is the value. So now I can see that exact concrete values, the raw data that I added can be visible. So based on this, equipped with this information, I will know, okay, there's a thread, there's a hash map, it has this kind of a structure. So by equipped with this information, we can go ahead and fix the problem. Okay. So now coming back here. So friends, what is the solution to this memory leak? Right? Once you're inserting the records, and then after that, you're changing the keys. How to mitigate this problem? You can mitigate this problem by declaring the key as a final, right? Say, what do I mean by that is, so you can come here, and if I'm going to make this as final, that means if I make it as final, that means this key cannot be changed. Once it is initialized in the constructor, after that it cannot be changed. If it changes, it will be raised as an error. See, look at this. The moment I change this, Eclipse is complaining me with this error. Do you see? Now I changed it. This field, the final field cannot be assigned. It's reporting this error. So this mitigates changes to any keys. See, earlier, say if I want to remove this final, say I remove the final, see the error is not there. So this will be a very valid check to mitigate, which will not allow the users to change the keys. So this is the best practice that you want to follow. Whenever you're using any object in the collections, it will be the map, set, anything, don't change once the keys are created. Okay. So this is the solution. Now, let's go to a next problem. Not so common memory leak problem. Time-taking finalize method. Friends, what is finalize method? What is a finalize method? Friends, here I can write, say there is a customer class. I can write a finalize method, right? So in this method, I can write any cleanup code. Say, suppose I want to, I open some backend connections. I open some file descriptors. I open some resources in my class. And in this finalize method, I can write code to close those connections, close those files. I can write the code to close those resources that I open. And when will this finalize method be executed? This finalize method will be executed right before that object is going to be garbage collected. Let's say customer object I created, I used it, and now it is garbage. No one is referencing it, right? And now when the garbage collector is going to remove this customer object from the memory, at that point it's going to go, and then it's going to execute this finalize method. So there I can go ahead and I can close all the resources that I want. Right? This is the this is how the finalize method is used in Java programming language. But friends, this finalize method has to be carefully used, right? Why, right? Let's look at this. If it's not used carefully, it can affect your application's availability. Let's look into this example. Here I put together this hypothetical example. Look at this, my friends. So here I have an object called a slow finalizing object, right? Now let's see, whenever this object is instantiated, I'm creating a very large string. Look at this. Here I'm creating a string which is of very large size. I'm creating almost like you can see I'm keep on appending xxxx. So I'm creating a very large string, and then I'm assigning it to this member variable. I'm not doing any operations here, right? I'm not doing any operations. But here when I say finalize, in this finalize method, what I'm doing is I'm just putting this thread to sleep for 5 seconds. So basically, I'm just trying to simulate that. Suppose I'm trying to close a resource. Let's say it takes very long time. I'm just trying to simulate it. I'm putting it to sleep for 5 seconds. Now let's see what this main method does. Main method doesn't do much. Here I have this while loop, just goes on a loop. Here, see what I'm doing. I'm just saying I'm creating a new finalizer object. I just keep on creating a new finalizer object. And then I create on the first iteration, I create an object. And then now I'm going on a loop. And now second time I'm creating an object. Third time I'm creating object. So what I'm doing is I'm constantly keep on creating objects. That's all I'm doing. But I'm not referencing this object at all. I'm not referencing this object anywhere. So once this thread, whichever thread is executing, once it completes this iteration, this object is ready for garbage collection. So for every iteration, I'm creating a new object. And once that iteration completes, immediately that object is ready for garbage collection, right? So now, friends, when I'm going to run this program, what will happen? I'm putting it to sleep. That's all I'm doing. What will happen? And this and every iteration, it's going to get garbage collected. So ideally, when I run, this program should be keep on running. But let's see what happens. I'm going to run this program. See, I ran. Immediately, just after creating like a few objects, 40 plus objects, it is resulting with out of memory error. Why is that? Okay, see here, I'm putting it to sleep. See, friends, pay attention. I'm putting it to sleep. Okay, so that means if it's taking time, let the response time slow down. Why sleep is causing the memory leak? Sleep can degrade the response time. But why it is causing out of memory error? Why is it? Is my question is clear? The sleep can slow down the operation, but why it's causing the out of memory error, right? So friends, to understand this, we have to answer this problem, we need to understand how JVM executes the finalize method. This is very important concept to learn. So we need to understand how JVM executes the finalize method. So now let's look into that. Friends, whenever you write a finalize method, JVM has a queue. JVM has an internal queue. In memory, it has a queue. And that queue is existing in this finalizer object. So there is a class in Java called as a finalizer. And this class has a queue. So here's the source code, which is there in GitHub. Let's look into that. Okay, look at this. This is the finalizer, which is there in the JVM. It has an queue. Look at this. It has an in-memory queue. It has an in-memory queue. So now let's come back to our source. It has an in-memory queue. So this queue is going to be empty when the JVM starts. When the JVM starts, the queue is going to be empty. But friends, look at this. Whenever, I don't know why. Okay. Whenever you write an object which has a finalize method, so as a developer, I'm writing object which has a finalize method. If it has a finalize method, and if that object is ready for garbage collection, that object gets added to this queue. That object gets added to this queue. It's get added to the in-memory queue. Okay. And then there is going to be a finalizer thread. A JVM has an internal thread called as a finalizer thread. This thread goes through every object in the queue. And then it's going to invoke the finalize method. It's going to invoke the finalize method. And once it is done, say it closes all the resources which has been used, which has been there in that finalize method, then the object it will be garbage collected. Then the object will be removed from the memory. But now, friends, look at this. What's going to happen if my finalize method is taking very long time to complete? In this case, it takes 5 seconds to complete. Taking 5 seconds to complete. That means this finalizer thread is going to be stuck for 5 seconds. When it's stuck for 5 seconds, but at the same time, this queue will start to build up, because any object in my JVM which has a finalize method, it's going to keep on added to this queue. So queue is going to start to build up. So it's going to take 5 seconds for me to complete this executing this method. And now the thread, when it comes to the second method to execute, by the time the queue is starting to build up. So when queue starts to build up, and when it goes beyond your XMX limit, then you are going to be slapped, then JVM is going to slap us with out of memory error. So that's what is exactly going on, right? Okay. Right. So there's a queue, and this queue is starting to build up because of the slow finalize implementation. So when this queue size starts to exceed the limit, XMX limit, we are being thrown with out of memory error. That's what is exactly happening here. Okay. So now when this happens, on this program, I captured the thread dump. I captured the heap dump. Now let's look into that heap dump. right? What I captured. So now let me go. Let me upload that heap dump. So here is that heap dump analyzer, heap hero. So here I'm uploading this heap dump file, which was captured by this program. So now it is uploading. It is analyzing that. So in a moment, we are going to see the result. Okay, so now we got the result. See, now it is reporting, oh, there is this class, Java lang ref finalizer. This is nothing but, this is the class, Java lang ref finalizer. This class is occupying 95% of memory. Examine what's going on, right? See, once again, come here. As I told, always the first object is what causing the memory leak. Right? So here there's this object which is occupying like a 95% of memory. So if you want to see what are its children, what does it contain, click on the list objects and click on the outgoing references. So I can see what are the contents of this finalizer. You can see this finalizer as this queue. Look at this. So this queue, see, okay, so this queue, look what is there. It has this slow finalizer object. This is that object that we are creating, right? You can see this queue is made up of all these slow finalizer object. So they are taking time, right? So that's what is causing this out of memory error. Okay. Making sense? Yeah. So friends, what is the solution to this? See, finalize. So since it is very risky, the JDK, they themselves have deprecated the finalize method because of this inherent flaw in it. There is only a single thread, finalizer thread, which has to execute all the elements in the queue. And if developer has poorly implemented, the thread is going to stuck. So this is an inherent problem in JDK. So the JDK developers recognized it and they have deprecated the finalize method. It's still available. Still you can use it, but it has been deprecated. So here are the alternate solutions for us instead of using the finalize method. What you can do, you can use the try with resources option. That is, you can use the auto closable, or you can use cleaner. So this is a new implementation which is meant to replace the finalize method. So this doesn't have the problem that what we discussed just now. Or you can, or in the code itself explicitly, you can say close the connections. You can explicitly cause the cleanup methods, right? So these are three potential alternate strategies for you to use other than the finalize method. Okay. Okay. So now I'm moving on to our third not so common memory leak scenario, which is the uncleared thread local variables. Okay. See, friends, what is thread local variable? What is it? Friends, have you seen this in your application logs? In our application log, see, this is our developer. As a developer, we write the code. We say starting the authentication, right? This is how I code. When I say starting the authentication, it gets printed. But how is this transaction ID printed? How is this transaction ID printed? First question. How is this printed? Because I'm not passing this transaction ID as an argument. And that too, another very important thing to understand, this transaction ID is unique for each transaction that comes to our application, right? Say for transaction A, it would have one ID. A transaction B, it will have a different ID. How is that? And in fact, I'm not even passing this transaction ID in my logging methods. But how it's getting printed? And that too, it's dynamically changing. How is that happening? Have you guys ever wondered that? Friends, this is achievable because of thread local variables. It is a very powerful mechanism. But just they say in that Spider-Man dialogue, with great power, you get great responsibility, right? So very powerful things, but all the powerful things has to be handled very carefully, right? So this is fair. How do we print this transaction IDs without even passing it as an argument? And that too, it changes for every transaction. It is because of a thread local variable. So what is thread local variable? Let's look into this. Friends, in Java, there are different types of variables. One is a local variable. That is, say there is this method. Within this method, I declare a variable. So it's only visible within this method. It's a local variable, right? And then I have a member variable or instance variable. Let's say there is this car class. To that class, to that object, I can declare a variable, right? It is a name, so that the entire class can see that. And then also, I can declare a static variable. So it means not specific to that object, but for that entire class, it is visible, right? These are commonly used. This is what we commonly use. But there's also this uncommon thing called as a thread local. So I can declare it like this, the thread local. I can declare a string or whatever this can be anything. It can be a string, integer, float, or my custom object. I can declare anything. So when you declare it like this, kind of a thread local variable, then what will happen? That variable will be set to that particular thread. Let's say a thread 1 comes, so that variable will be set to that thread 1. So if thread 2 comes, you will not be able to see the value of the thread 1, what was set for the thread 1. So thread local, as the name says, it is just local to the thread. Only that particular thread can see it. So what happens in our logging frameworks and all, when the new request comes, they use this thread local variable and they set a unique ID for the thread alone. For thread alone, they set that unique ID. They set it at the very front, right? Once they set, let's say now this thread, now executes method 1. So this is the ID I set. So now this thread 1 carries this ID with that. So now it comes here. So this ID is visible. And now, let's say from here, the thread goes to class B method 2. It goes to different method. Now that ID also carries with that. You don't need to explicitly pass as arguments. It is embedded within the thread. So it is here. So now from here, so let's say thread goes to class C method 3, a different method. This thread local variable goes along with that, right? So you don't have to explicitly keep passing as arguments. It goes within the thread. Once you set, it's available within the thread, right? So this is that. So since it is available within the thread, the logging frameworks like a log4j, they take it from the thread. They take it from the thread and then they print it into your log file, right? This is not only log4j or any logging framework, like a lot of like Hibernate and all, they use this thread local exhaustively, right? Okay. So now let's look into a live example of this thread local, right? How we are using it, right? How to use this and what was triggering. So I made an example which causes a memory leak because of this thread local. Okay. So friends, look at this. This is the thread local memory leak, right? So here I'm creating a thread local variable. Here I'm creating a thread local variable, right? Now look at this. What I'm doing here, there is this main method. Let's focus here. There is a main method. Within this main method, I'm saying while true. That means I'm going to infinitely, I'm going to go on this loop and then I'm going to be creating new thread objects. I'm going to be creating new threads. Within this thread, what I'm doing, I'm now setting a thread local. I'm now setting a thread local here. So I'm saying a thread local. I'm saying a string 1 and then this text. So this text is basically, I'm just creating a very large string. Like say I'm just creating XXXX. I'm creating a very large string here. And now I'm setting as a thread local variable. And then I'm putting this thread to sleep. I'm setting the put to sleep. Like this, I'm just keeping on a while loop and I keep on creating new threads. So now let's say I keep on creating new threads. Now friends, what happens? I'm setting this as a thread local variable. But if you see, I'm not removing this thread local variable at all. I'm not removing it at all. So that means the thread local, once it's set, it will remain there. I'm not removing it after its usage. So, but think what will happen in our application, we have hundreds of threads. So in each thread, if you're setting the thread local, and you're not removing it once its usage is completed, but the thread will remain in memory. So when threads will remain in memory, that means the thread local variables will also going to remain in memory. If they start to build up, you're going to get out of memory error. So let me run this program. See, I'm running this program. See, it says it started, see, whenever I'm printing, okay. It was able to create like a 44 plus threads. And after that, it is throwing this out of memory error because I'm never removing this thread local. Now let's do, just for fun, what I will do. Now let's say, I'm going to remove this thread local. I'm going to say thread local string dot remove. Say once I'm setting, so after the usage is completed, I'm just saying remove. I'm doing this. Now let me run the same program. Let me run the same program. You can see when I ran, you can see the thread is keep on going. Because I'm after usage, I just keep on deleting it. The program can keep on running for infinitely because I'm legitimately using this. And friends, it's very common to forget removing the thread local variables. It's very common to forget removing the thread local variables. So you can see the program keeps on continuing, right? So, friends, let me stop. So just for the sake of completeness, we'll look into the heap dump that was captured from this program. So let's look into this heap dump which was captured from this program, and then let's analyze that quickly. So okay, for the 1.7 I upload, see here it's saying like these many instances of threads are there, and together they're occupying like a 97% of objects. See, friends, I was telling, I explained this in my previous webinar, but I would like to touch upon it here also. Friends, when a memory leak happens, there is only two possibilities, my friends. There's two type of patterns are possible, right? When a memory leak happens, there is only two possibilities are there, right? Let's look into what are those possibilities are. The first pattern is there is one single object which will keep on growing in the memory. It will keep on growing in the memory. And when it goes beyond that XMX limit, you're going to get out of memory error. Like the hash map example we saw, right? In the hash map, the key was mutating and it kept on growing. And once it kept on growing, it would crash with out of memory error. This is the pattern number one. And there is another pattern. It is there will be a one single object. That single object will keep on multiplying. It will keep on multiplying. When it keeps on multiplying, then also when it goes beyond the XMX limit, you're going to get out of memory error. So it is either one object keeps on growing or there is a one object keeps on multiplying. So these are the only two possibilities for the memory leak to happen. So the previous two examples that we discussed in this webinar was of the pattern where one single object was keep on growing. Whereas here, if you see what's happening in this example, there is a thread keeps on multiplying. A thread keeps on multiplying, and then you're getting the out of memory error. And when this happens, you're going to see look at your largest object. It will not be a one single object which is going to be occupying a lot of space. Here you're going to see multiple objects of the same type occupying the space in memory. So this is what that is. This is the second pattern, live in action. Okay. Okay. So friends, just to take a, so what are the, how do you, wait, no, not here. So what is the solution for this thread local memory leak? That is, you want to say thread local string dot remove. That is, you want to remove the thread local after usage. Okay. So friends, now in this webinar, we spoke about three scenarios of one is that hash map, mutable keys, with which it was growing. The second one was the time taking finalized methods. And then the third one is the thread locals not getting removed. Right? We discussed this, and we also discussed how we went to go about troubleshooting these memory leaks, right? So this comes to end of my this month's webinar. We will, in case if you want to learn more about JVM troubleshooting and performance engineering, here there is this online masterclass that I offer. It is available. You can go ahead and listen to it at your preferred convenient timings, right? It has 9 hours of contents with coursework and homework. You're welcome to look into that. Okay. So friends, with this, we are coming to end of this month's webinar, right? But of course, I'm going to be here. If there's any questions, you're welcome to ask. I'm going to be answering it. But with this, we are coming to this month's webinar. Thank you everyone for taking your valuable time. We will connect and discuss with you in next month's webinar as well. Okay.